So, a short recap to begin today's discussion. So, we were talking about time dependent perturbation theory. So, we have a time dependent perturbation which is likely to cause transitions from one state to another, maybe from a ground state to an excited state or vice versa. And the Hamiltonian, the perturbation Hamiltonian is written as it's H prime m k, which is a function of t, and then we have a m k sine omega t. That is the perturbation that we have been talking about. K is the initial state where the system was before the perturbation was switched on, and m is say an excited state, or a different state than compared to k. And we are going to talk about computing this coefficient. So, that is related to the probability of making a transition, for the system to make a transition from an initial state k to a final state m. We could simply say that it is a final state, and if we are resorting to a first order perturbation theory, we will put a 1 here, and that is going to be the thing or the quantity to compute. And this is what we have found yesterday, or rather the last discussion that we were having, that is, so this is equal to I a m k and 2 h cross and exponential I t naught omega m k plus omega and minus 1 and omega m k plus omega and exponential I t naught omega m k minus omega minus 1 and omega m k minus omega. And so, it consists of two terms. The first term is called as the absorption term, which we will see immediately. The second term is called as the emission term, and we will talk about these separately. In fact, we are going to concentrate mostly on the second term, which as I said, that it is related to the emission, that is transition from one state to another. Let us look at each one of the terms. So, the denominator of the first term. So, 1 is first term in RHS, that is inside the bracket. Okay. So, then the poles of that, poles means where the denominator becomes 0, that is, this is the condition, and omega m k, as we have said, that it is E m minus E k over h cross plus omega equal to 0. So, that immediately tells us that E m equal to E k minus h cross omega, which means that E m is less than E k, and so E k is the initial state or the unperturbed level before the perturbation was switched on. So, what it means is that the H prime m k, which is of course related to the a m k and so on, it carries away energy. And so, it is related to the absorption. So, the field is absorbing energy from the system. So, that is why it is called as the absorption term, and let us look at the second term. And that term is of course, with a negative sign, it is minus I a m k by 2 h cross and I have an exponential I t naught omega m k minus omega minus 1 divided by omega m k minus omega and so on. We can write this, we can simplify this, we can write the numerator as a sine by taking exponential I t naught by 2 omega m k minus omega out. So, that gives this one, the second term with 1 exponential minus I t naught omega m k minus omega by 2. So, if we do that simplification, then we will and that way we can get rid of this I as well, because the sign in terms of the exponential comes with a definition which has a 2 I in the denominator. And once we do all that, which I leave it to you, it is a simple step to complete. So, this is H cross, and we will keep a I t naught by 2 omega m k minus omega, and so this is exponential. So, this becomes really a sine so, it is a sine, and then there is a t naught by 2 omega m k minus omega and divided by omega m k minus omega, and we just come back to this term. Now, look at the denominator. The denominator is of course, the denominator makes sense when or rather it has a pole when omega m k equal to omega, which means that E m now is E m minus E k, it is equal to H cross omega, and that tells us that the E m is greater than E k, which means that the H prime m k or the perturbation term is it pumps energy into the system, and this is related to emission. Okay. So, now, so basically we will more concentrate on this rather than on the first term, because this term makes a large contribution close to the resonance, that is when omega m k becomes equal to omega, and in any case both terms are equally important. Let me just with a diagram, let me explain that. So, this is your omega axis and this is omega equal to 0. Now, I have a plus omega here and a minus omega here. So, these are so there is a plus omega and a minus omega. So, there is a line which are, so this corresponds to the emission line or the second term, and this corresponds to the absorption and that is the first term. Now, of course, these are the spectroscopic lines, or these are the lines that will show up in experiments, and these lines cannot just be a very sharp lines which would of course, and the width of the line would depend on the basically the least count of the measuring apparatus, or the energy range over which it can measure sort of these, or rather see these lines. So, let me give a little bit of width to these lines. So, these will be the spectral lines that will be seen for each one of them, and let us just talk about these things to be delta omega and delta omega here as well, and this distance, or rather the two lines are separated by a twice of omega f I, which is so in this particular case, as it the way the figure is drawn, it is very clear that we need to consider one line at a time in the limit that your delta omega is much smaller than omega f I or 2 omega f I. So, if this condition is satisfied, then only we need to look at one of the lines at a time, and maybe at this moment let us just consider that we are concentrating on the second term, which is the the resonance term. The other term is called as the, which is in the negative minus omega. So, that is called as the anti-resonant term. So, they are symmetrically placed about 0, and at this, as I said, that we are just going to talk about the resonant term at this moment. And let us tell this call this quantity, let us just write with a different color. So, let us call this quantity as alpha, okay? And in which case the CM1 T mod square is equal to AMK by H cross square, and there is a sine square alpha T naught by 2 divided by alpha square. So, that is the form of this, and let us in addition take beta equal to alpha T 0 by 2. So, then this thing would be written as A m k by h cross square sine square beta by beta square, and since we have taken T 0 by 2 whole square common, that had to be multiplied here. So, we will multiply it. So, T 0 square by 4, and that will be there. Okay. So, this is our form of the transition amplitude, which is related to the probability of transition from initial state k to a final state m, and this quantity sine square beta by beta square is called as the sinc function, and the sinc function, or the square of the sinc function sine theta by theta is called as a sinc function. So, this is if we plot it, it looks like that now the square will never become negative. So, it will look like this resembles the diffraction pattern that you may have seen in optics. It is nicely symmetric. You might not have drawn it accurately, but it is it has to be, you know, I mean a little sort of all right. So, this is so I am plotting a sine. So, this is my CM1 T square, and this is as a function of so alpha. In fact, this is like sine square beta by beta square apart from these factors, or you can take it to be proportional to this. So, this is proportional to this. This is actually sine square beta by beta square versus alpha that is being plotted. So, this is at alpha equal to 0, and this is at 2 pi over T 0, this is at 4 pi over T 0, this is at 3 pi over T 0, and this is at 5 pi over T 0, and so on so forth. All right. So, this is a plot that we are plotting sine square beta by beta square versus alpha, and so pi by t 0 corresponds to this entire thing a m k by h cross square t 0 square by pi square t 0 square by 4, and so 3 pi by t 0 will corresponds to this entire thing divided by 9, and at 5 pi by t 0 it is so at 5 pi by t 0 it is it corresponds to this entire thing divided by 25 and so on. So, if you see this, the area under the curve, which is of course related to the probability of transition, it is proportional to t 0 because the height goes as 1 by t 0 and this alpha is and then of course, it is there is a t 0 square that is there and there is a 1 over t 0. So, this multiplied by 1 over t 0 will give a t 0. So, that is the transition probability, and the so area under the curve, we will write it here. So, area under the curve transition probability. Okay, so let me. So that is the transition probability, which goes as of course, as t 0. All right. So, let us just give a physical picture that what is happening. So, you have two level system here, call this as a phi f, which is nothing but that m by the index m, and this is a phi I, and so this is that term number 1, that is the absorption term or the anti-resonant term, and for the other one it is the phi f and a phi I, and so there is a particle that makes a transition from phi f to phi I, and that is the second term which is related to the emission. Okay. So, that is the physical picture for these two terms, and of course, we are more interested in talking about this the emission term that we have talked about. So, of course, the emission term is more important that is we can neglect the absorption term when as I said earlier that 2 of omega f I, we can put it inside a mod sign, that is it does not matter which one is bigger, that is the final state energy is a bigger or the initial state energy is a bigger. This has to be much greater than delta omega. Now, delta omega, that is the line width, depends on the time duration for which the perturbation is switched on. And if we simply go by the order of magnitude using or an estimation rather using Heisenberg uncertainty principle, then this can be simply written as 2 pi over t 0. So, just to remind you, t 0 is the duration for which the perturbation is switched on. Okay. So, that means that the T 0 has to be much greater than 1 by omega f I, which of course, at resonance it is equal to 1 over omega, which means that the additional restriction of neglecting the anti-resonant term is that the perturbation term must go through several cycles in this interval 0 to T 0. Okay. So, that is the additional restriction that we have. Now, if the T 0 is of the order of 1 over omega, we have a situation where the perturbation is linearly varying with time, and in which case it is not possible to neglect or rather separate out these two terms such that we can concentrate on one at the expense of another. So, we will take this to be true, that the perturbation term must go through several cycles. So, it is rapidly oscillating during the time that the perturbation is switched on. All right. Now, this has been told earlier, it could happen that during the course of transition, the particle or the atom goes on to a state, the final state is a part of a continuum, which means that it is not a single well defined state, it is a sort of collection of many states, and it is a continuum which forms a continuum by having many energy levels having very close by values. All right. In which case we cannot talk about a probability of this transition, and rather we should talk about the probability density of transition, and this probability density should be integrated over in order to get the total probability integrated over all possible energy states that lie in that in that range. So, coupling with states of the continuous spectrum. Okay. And so, if the final state falls into a continuum, okay. And so, phi f is not well defined. So, the probability density will be given by phi f and psi t mod square, and this probability density has to be integrated over. And how does it arise? It arises, consider a collision event in which a particle with an initial momentum p I, p I, which means that the energy E I equal to p I square 2 m, we are talking about a free particle, and this particle after the collision gets scattered onto a final momentum P f. And now the detector by which it is being captured has a finite angular aperture, and the energy selectivity or the sensitivity may not be perfect, and in which case we talk about the solid angle of the detector, which or rather detects this particle, and this gives so this owing to finite energy sensitivity, the detector measures energies in a solid angle, or momentum rather, we should talk about momentum. In a solid angle d omega, and that gives so basically the final state energy, so which means that it is between some E f and E f plus d E f is the detection takes place. In which case we will have to actually count the number of states which falls into that continuum of states between E f and E f plus d E f, and so the probability p of say phi f t, it should be sum over all these final states, and then it is a phi f psi t and square. Now, this sum over f, that is the energy states that lie in that range E f to E f plus d E f, is nothing but the density of states corresponding to that final state energy. Hence, this p of phi f and t has to be integrated over, and one gets a phi f and a psi t mod square and a rho epsilon d epsilon, and this is the final result for that probability for a system to make a transition from an initial state to a final state in presence of a time dependent perturbation. So, we are now equipped to talk about the Fermi's golden rule, and let us see what it means in the present context, that is including this density of states for the final states and so on. So, let us so, let us take again a sinusoidal perturbation of the form that we had taken. So, we had taken this h prime to be or rather h prime m k to be equal to a m k sin omega t, that is what we have been discussing, and now we let us call it as a p f I t, just the same thing as what we have written as the transition probability. It is nothing but a m k. A m k is in general Hermitian. So, which means a m k equal to a k m star and so on. So, this divided by h cross square and a sin square beta by beta square and a t 0 square by 4, and beta equal to omega f minus omega I divided by 2 into t. So, it is alpha into t, and hence this is what we need to calculate, and then we, if you wish. So, this is that p f I t. Now, this p final state phi f t is equal to 1 by h cross square d epsilon rho epsilon and phi f h prime phi I square and a sine square beta by beta square, which is just again writing this a m k, where just try to connect that m is equal to the final state and k equal to the initial state. Okay. So, this is implicit here, and now we have to perform this integral. Now, in order to perform this integral, it could be quite complicated, because there are in fact 3 terms which all depend upon the energy, that is the term which is here, the term which is the density of states, which depends upon energy, which is usually a smooth function in most of the cases that we are accepting. In some pathological cases where this density of states show a divergence close to some bandage or some such thing. This is the matrix element square, and this is that sine square beta by beta square, or the sinc square function that we have obtained because of the time dependent perturbation. Now, it is not too difficult to understand that both these quantities are somewhat slowly varying quantities. The only quantity that varies very rapidly for the resonant term, we are talking about just the resonant term, is this quantity, that is the sine square beta by beta square. And this sine square beta by beta square, if we just go on to see your the plot that we have drawn earlier, it is this. So, if you see this, you see the major contribution of this probability density would come from this central peak, and the auxiliary peaks are of course there, but they are down by a factor of 9 or down by a factor of 25. So, they are not as important as this, and because of this close to resonance, we can sort of replace it by a delta function, okay, with the width which is very small, and that width of course we will talk about that width. But the fact that the sine square beta by beta square can be replaced by or by a delta function, that one has to be convinced about first, and this is what I am trying to impress upon, that in this particular this term or this integral that we are talking about, the one that is most important is the sine square beta by beta square. Okay. So, if we are trying to replace it by a delta function, see what are the conditions corresponding to that. So, let us take this limit t tending to infinity, sine square beta by beta square is nothing but a delta function up to a constant factor, which is E minus E f I, or we can simply write it as epsilon minus, which is a general energy, and this is 2 pi h cross t delta of E f I minus E. Okay. So, this is just like that limit epsilon tending to 0, sine square x over epsilon divided by x over epsilon is can be replaced by a 4 pi by epsilon delta of x, and just you try to connect that x by epsilon is equal to alpha t by 2 in our case, where x is equal to alpha and epsilon equal to 2 over t. Okay. So, the main or the summary of this discussion is that we are going to replace this sine square beta by beta square by a delta function, which is the singularly most rapidly varying function. The other functions are somewhat slow varying and can nearly be taken as constant in the vicinity of resonance. Okay. And this delta function has got a width which is given by 2 pi h cross over t, and So, in this width we are going to talk about the density of states. In that energy width, how many energy states are there that need to be incorporated in calculating the transition probability. So, that is actually encoded into our rho epsilon d epsilon. So, let us just introduce that we are interested in talking about the transition probability per unit time. Which is equal to 1 by T 0, and then we have a C k T mod square. Okay. Let us just write C m, because this is what you are C m T square, and if we are talking about the first order perturbation theory, we will have a 1 on in the here, and then it is integrated over all final states. Okay. And of course, these m lies into in the continuum. Okay. So, we will introduce as we have said that we will introduce density of states. We can write it as a rho m, which is between epsilon m and epsilon m plus d e m. Okay. So, a w will be 1 over T 0 d e m rho m C m mod square. Now, the d e m equal to d of epsilon k, or rather epsilon m minus epsilon k minus h cross omega. This is, as we said, that it is for the resonant term, and this is equal to a d of omega k m minus omega h cross, and this is equal to a d of omega k m minus omega and multiplied by a T naught by 2, just to make it look like a beta that we have introduced, and there is a 2 h cross by T 0. So, this is equal to a 2 h cross by T 0 T b d beta. So, the transition probability per unit time becomes equal to 2 pi by T naught and a d beta rho m, or we can, I mean, instead of writing it as rho, so we can write it as rho epsilon m and a k m mod square. A m k and a k m are same, as I said that they are mostly Hermitian. So, it is sin square beta by beta square. So, this is a much slow varying function as compared to this. This is a fast varying function. Okay. So, this is what it is. So, these are the transition probability per unit time, and then of course, we can write this down as, so this W is equal to 1 over 2 h cross. We take this thing out and take its average value, since this is a much slowly varying function as compared to the second one, then we take this and take an average value of these two terms and take them out, and let us write them as a rho epsilon m and a k m square and a minus infinity to plus infinity, that is sin square beta by beta square, and there is of course a d beta. Now, this has a value, this integral has a value, that value is equal to pi. Okay. So, this becomes simply equal to pi over 2 h cross and this rho. Now, I can also split this two terms, and so this is a k m mod square by 2. So, the average value of these matrix element can be written as a half of the of these a k m square, and so this is equal to, simply equal to. So, if we write it in words, it is equal to the transition probability per unit time is proportional to the density, average density of states, we write it with a DOS. So, DOS means DOS is for density of states for the final continuum of states. So, it is average density of states and multiplied by the square of the matrix element of the perturbation term between initial and final states. Okay. So, write it with this thing, and let me just box it once again. This is called as the Fermi's golden rule. All right. So, this is the Fermi's golden rule, and it is applicable to a variety of situations, especially say the ionization of the hydrogen atom in the ground state. So, when hydrogen atom or the electron in the hydrogen atom is in the ground state, and if it is somehow given an energy which is equal to 13.6 electron volts, that is the magnitude of the perturbation or the time independent part of the perturbation, that is the matrix element AMK. If that is of that order 13.6 electron volt, then this electron will be ejected, or this hydrogen ion will be ionized, and this electron will go on to final continuum of states, and the final those density of states of those final continuum of states will have to be taken into account in order to calculate the transition probability per unit time, and it has also to be multiplied by the average density of states of those final states. So, instead of doing that, which is ionization of hydrogen atom, let us give a short introduction to the lasers, or which is a part of a big or rather discussion called as the interaction of radiation with matter. We will not do that very rigorously, but we will just introduce the AB coefficients, and we will tell you that how to calculate these coefficients, Einstein's AB coefficients. Okay. So, let us again define a two level system. Okay. This is called level 1 and this is called level 2, and this is called the A12, and this is called I will write it with a dotted line, which is called as a B12, and will also write with another dotted line, which is called as a B21. So, it is just the final state is written first, and then the initial state is written. So, so these are called as the Einstein's A-B coefficients. So, where so these are called AFI and BFI. So, they are AFI and BFI. So, the A coefficient, it stands for spontaneous emission. Okay. And the B coefficient stands for induced emission, also absorption, will tell you what, and in which case the first term that we had neglected in that original expression will have to be brought back. So, the transition probability for induced emission, for spontaneous emission, say first spontaneous emission is equal to B12 u omega. Let me just write that u omega is the energy density, or so let us have a u omega is the energy density per unit frequency range, that is between, or you can say u omega d omega to be the energy density between omega and omega plus d omega, which is a better representation. So, we will talk about u omega d omega together, which is the energy density in the range in the frequency range omega and omega plus d omega. So, the transition probability for spontaneous emission is this. I am sorry, this is not for spontaneous emission. Spontaneous emission does not depend upon the energy density, it is simply equal to A12. Now, the transition, so this is number 1, number 2 is transition probability for induced emission. It is equal to B12 u omega, and third is transition probability for induced absorption. Once again, to remind you that this is the first term that we have talked about earlier. So, this is B21 u omega. So, these are the nomenclatures of these A-B coefficients, and let us see that at steady state the number of upward transitions is same as the number of downward transition. So, that tells that N2 multiplied by A12. So, that is the number of atoms making a transition from 2 to 1. So, that is N2, and N1 is the number of atoms making a transition from 1 to 2. So, it is A12 plus B12 u omega, this is equal to N1 B21 u omega. So, I can write that A12 plus B12 u omega equal to n 1 plus n 2 b 2 1 u omega. So, as E 2 minus E 1 equal to h cross omega, one can write down from the Boltzmann distribution n 1 by n 2 is equal to exponential E 2 by E 1 beta or by k t, which is equal to exponential h cross omega by k t. So, that is n 1 by n 2. So, a 1 2 plus b 1 2 u omega equal to exponential h cross omega by k t b 2 1 u omega. So, u omega is equal to a 1 2 divided by exponential h cross omega by k t b 2 1 minus b 1 2. Now, in order to find these coefficients, we can do a comparison with Planck's law of blackbody radiation. And where u omega is given by some constant quantities such as this, and the Bose distribution follows here. And so, comparing let us call this as 1 and 2. So, comparing 1 and 2, B 1 2 is equal to B 2 1, which says that the probability of induced emission and absorption are the same. So, from 1 can get u omega equal to a 1 2 divided by b 1 2. Now, since they are same, one can simply write it as h cross omega by k t minus 1. So, a 1 2 divided by a b 1 2, it is equal to h cross omega cube by 4 pi square c cube. So, that tells that a 1 2 equal to h cross omega cube by pi square c cube and into b 1 2. So, there is actually one coefficient out of those 3 which is independent, because the 2 of them are equal and one of them has a relationship with another. So, one independent coefficient. Okay. So, the last thing that one can see here is the following, that if we want to prove that these B 1 2 equal to B 2 1, how that comes about in a more rigorous way, then let us talk about the absorption term in presence of the time dependent perturbation. So, absorption, so which means that m equal to 2, k equal to 1. Okay. And so, a C 2 t in our original language is equal to minus I A 2 1 by 2 h cross exponential I t naught omega 2 1 minus omega minus 1 divided by omega 2 1 minus omega. So, that is the C 2, and the emission term is m equal to 1 and k equal to 2, and so that is the C 1 t is equal to a plus A 1 2 by 2 h cross and exponential I t naught omega 1 2 plus omega minus 1 omega 1 2 plus omega. So, we will prove that C 1 t mod square equal to C 2 t mod square. So, C 1 star t can be written as, so C 1 star t can be written as minus I A 1 2 by h 2 h cross exponential minus I t naught omega 1 2 plus omega minus 1 omega 1 2 plus omega, that is also omega 1 2 equal to minus omega 2 1. So, that makes the C star t is equal to minus A 1 2 star. Okay, so, I should make it star as well. Knowing that these are Hermitian, we can change it. So, 2 h cross and exponential minus I t naught omega minus omega 2 1. So, that is and minus 1 divided by omega minus omega 2 1. Since H prime is Hermitian, A m k is equal to A k m star, which has been already told. So, it is one can see that now A 1 t mod square equal to A 2 t mod square, and since A 1 t mod square is proportional to B 1 2 u omega, which is the emission term, and A 2 t is B 2 1 u omega, which is the absorption term. So, B 1 2 equal to B 2 1. Now, microscopic derivation of these coefficients, we have not derived this coefficient, but those coefficients are very easy to derive from whatever we have done, and each of these we know now that there is just only one coefficient that is unknown, and that coefficient can be determined exactly in the same way that we have calculated this these transition probabilities. The only thing that we need to know is that the H prime which will come from the interaction of radiation with matter, and we will do it in a tutorial problem, this interaction of radiation with matters and what is the Hamiltonian for that. What you need to know is that a priori, without going into the details, that the canonical momentum now changes from P to P minus E A, where A is the vector potential which gives the magnetic field which the B equal to curl A, and of course, there is a gauge choice of gauge that could be also discussed there, but other than that we now have all the necessary tools to calculate the transition probability, which is only a feature of the time dependent perturbation, as has been stressed many times before. And so, as I told that it can also be used to calculate the AB coefficients. Now, we just need to know one coefficient and the rest will follow, or we can also calculate the ionization of hydrogen atom by using this time dependent perturbation theory.